This is lecture 18 of condensed matter physics 1. And we have been discussing about crystal structure, and this week I am focusing on X-ray scattering from crystals. I am going to start this lecture with some repetition of yesterday's lecture, because we want to develop different ways of looking at the same thing and then go on to present what Wigner-Seitz cell is, what Brillouin zone is, and then develop theory of X-ray scattering. So, yesterday when I was discussing the scattering of X-rays, I made this picture where there was one scattering center here and the other scattering center up here, with a distance between the two connected by vector r, and I had a incoming k in and outgoing k out, and we wanted to get the phase difference between the two. The phase difference is given by the distances here, this distance plus this distance, and if you look at this angle, this is r, this is k in, this is k out. This angle is pi by 2 minus theta, where theta is the surface perpendicular to r, and this angle is greater than pi by 2. So, when I added these two distances out here, this is r sin theta, this was r sin theta prime, then what I got, because this second angle with k out is greater than pi by 2, the phase difference I got was k in dot r minus k out dot r. This minus sign comes because of this angle being greater than pi by 2, although it appears that the two distances are adding. This may be a little confusing, so I am going to give slightly different picture today, so that this is very clear. So, this is k in, and from lower side to the upper side is r, and I am going to make k out so that that angle remains smaller than pi by 2. Then you notice I am going to erase this r so that I can complete the line. Then you notice that the difference comes out here as r sin theta and out here as r sin theta prime, but in the case of incoming X-rays, the difference adds, and in the case of outgoing X-rays it subtracts. So, again you get phase difference is equal to k in dot r minus k out dot r. So, I am giving you a slightly different way of looking at it. Both are equivalent. The first one expects you to realize that the angle is greater than 2. So, that minus sign is picked up from there. So, I thought I will just clarify that further and give you a different way of looking at the same thing. The other question was when I looked at scattering from an atom. So, from a single atom, when you look at the scattering, the wave psi r is equal to psi n, which is I k n dot r, plus scattered wave, which is f r over r e raised to I k out dot r, and this one goes out spherically. So, this is usually written as e raised to I k in dot r plus f r angle r e raised to I k out r is going out radially. And then what I did is, if I take position of the atom at r I, then I wrote the scattering amplitude or scattered amplitude as, so let me just repeat myself. Here is the atom, psi r is e raised to I k n dot r plus f r over r e raised to I k out r, if it is spherical, otherwise it is k dot. Then if I take the atom position as r I, then the scattered wave is f, I will write this as r unit vector prime divided by r prime e raised to I k dot r prime, where r prime vector is r minus r I, and therefore, the scattered amplitude is f, that r prime over, if r is much greater than the atomic position, I wrote this as r e raised to I k n plus delta k dot r minus r I. And then I said this actually goes over to e raised to I k out dot the phase picked up is e raised to I delta k dot r I. So, what happens to other terms? Let us see the terms we have left. One term is e raised to I k n dot r. This is independent of I, so it comes out when I take the sum. The other term is e raised to I delta k dot r, again independent of r I. Third term is e raised to minus I k n dot r I, and fourth term is what we have written out here. How do these terms cancel out? So, when I take the sum over I for all the atoms, f r I prime over r, then I have e raised to I delta k dot r I. Then I have the other terms. So, outside terms are going to be this term which comes out, and when I take the amplitude, this just goes out, it cancels. This term, when I take mod amplitude square, this term also cancels. So, the two terms indicated above give 1. The third term cancels because you see this is only for the phase for only the outgoing wave. The incoming wave also picks up a phase e raised to, this was a minus sign, I delta k, k n dot r I, and that combined with this gives you 1. So, that is the other clarification I should give, that when I am considering scattered wave from an atom at position r I, the incoming wave has picked up a phase, and that cancels with the phase of outgoing wave at e raised to minus I k n dot r I term, and therefore, f for for psi for ith atom becomes f r I over r. These complex numbers e raised to minus I delta k dot r I. So, that is another clarification. Now, we go back to X-ray scattering and related concepts. So, remember we had defined Brillouin zone as the smallest unit of reciprocal lattice. So, this is also is therefore the primitive cell for the reciprocal lattice. Now, recall that primitive cells are not unique. Therefore, this is one of the ways, the way we made Brillouin zone, one of the ways how you get primitive cell. Now, there is a corresponding way of getting the primitive cell in real space, and this I had not done earlier. So, I am going to do it today, so that the two are related and they are sitting right next to each other. Corresponding way of getting primitive cell in real space lattice, and this primitive cell is called the Wigner-Seitz cell. So, what do we do to get the Wigner-Seitz cell? Steps to get a Wigner-Seitz cell. Take a lattice point and I will keep illustrating this with a rectangular lattice in 2D. So, if I have this rectangular lattice in 2D, I need one more. So, I will choose one particular lattice point. That is step 1. Next step, so we have taken step 1. Let me make this cell again. And I have chosen one particular one. Number 2, draw lattice vectors from the chosen lattice point to nearby lattice points. So, let me do that in what I have shown above. So, I am going to make these lattice vectors. Step number 3, draw bisectors. So, line in 2D and plane in 3D of these vectors. So, let us do that. I will draw these perpendicular bisectors. So, I should write perpendicular bisectors. So, these are going to be perpendicular. The bisector out here will be here, draw all these. And take the smallest cell. Obviously, it has to be repeatable, made by these, and this is the Wigner-Seitz cell. And since it contains only one lattice point, because you excluded every other point, this is going to be a primitive cell. So, this is a primitive cell, because there is nothing smaller than this which is repeatable and contains one lattice point. So, here if you look at it, this is how it is going to look like. Let us see, I think it will look like this. I may not be perfectly right, but you have to make it and see. I am just giving, this is an illustration. So, I am making what is coming out truly, may not be right, there may be only a hexagonal or something, but this is the idea. So, this is a Wigner-Seitz cell. Let us take one more example in 2D itself. Another example in 2D. The other lattice that I have is body centered rectangular lattice. So, the way it looks is, there are these points, and then there are points at the center of the rectangle. I will draw lattice vectors to nearby points. So, this is how they are going to look. And draw their perpendicular bisectors. So, this is how it is going to be here, this is how it is going to be here, this is how it is going to be here, this is how it is going to be here. So, this is going to be the this probably will meet here, hexagonal cell. Again, please check it, I may not be making it perfectly. So, this is the Wigner-Seitz cell for a rectangular lattice, body centered rectangular lattice. Let us take an example in 3D, and I am going to take a simple cubic Again, if I take a point and make all these perpendicular bisectors, here it is easy to see that it is going to be cubic. Again, more interesting would be body centered. Cubic. So, in the body centered cubic, I have this simple cube. I am going to attempt making the Wigner-Seitz here. I have these atoms at the corners and one at the center. Then I have these lattice vectors from here to all these corner atoms and also to the next cell. And I am going to make the perpendicular bisector planes here. So, let me erase these lattice vectors which I have shown. So, keep in mind that it is these lattice vectors whose bisectors I am now going to make. So, what you are going to have is a bisector here going like this. So, this probably is going to be a triangular bisector for all these. Let us see this one and this one here, all these triangular, one on the back side. So, what you are going to get here on the top is going to be one line like this, not on the face, but inside, one line like this and one line like this. And on these surfaces you are going to get a hexagon. On the back side you are going to get a hexagon for all these lines which are perpendicular to the diagonals. So, on this side also you are going to get a hexagon, and on the surfaces you are going to get these squares. So, this is a little complicated, right. So, in the front face also between this hexagon and the next hexagon, it is going to be a square like this, and these are along the diagonal. So, let me show it again. The BCC one is a little tough one. So, this is going to be a triangular like this, and here you will go to get a square like this, and on this, along this perpendicular to this diagonal is going to be hexagon, and so on. So, this is a little complicated figure. So, this is how you get a Wigner-Seitz cell. You should practice it more, and you can see it requires a little practice, right, and see how it looks. FCC is even more difficult. So, given this, let me ask you a question right here. And the question is, how would you draw the Wigner-Seitz cell for FCC? You sit, you practice, and you kind of get it. Do it, even if you get it wrongly, you will at least make a picture in your mind. Now, what is Brillouin zone? Now, let me write what Brillouin zone is. Actually, it is not Brillouin, it is Brillouin. Brillouin zone is the Wigner-Seitz cell of reciprocal lattice. So, once you have made the reciprocal lattice, which we talked about what the unit vectors are in reciprocal lattice, then you make the Wigner-Seitz cell there, following exactly the same process, and you get the Brillouin zone for the lattice. So, let me ask you a question here also. How would the Brillouin zone of FCC lattice look? So, first you have to realize that an FCC lattice has reciprocal lattice which is some kind, and the Brillouin zone therefore is going to be the Wigner-Seitz cell of that lattice. So, that is that. Now, we had talked about reciprocal lattice in the previous lecture, and what we had said was, given the regular lattice vectors A, B and C, the corresponding reciprocal space vectors are A 1 equals 2 pi B cross C over A dot B cross C, B 1 is equal to 2 pi C cross A over B dot C cross A, and C 1 is equal to 2 pi A dot B over C dot A cross B. This is in 3D. Question now I ask is, what about 2D? So, the question I am asking is, for a 2D lattice, for example, graphene, what is the procedure to get reciprocal lattice vectors, right? Because I cannot do that A dot B, A dot B cross C and things like those. So, let us see, if I have in 2D a vector, unit vector A and unit vector B. So, this is the lattice. How do I get the reciprocal vectors? So, what I would think of this as having a third lattice vector C perpendicular to it, and that will make a 3-dimensional lattice, and then make the reciprocal lattice vectors. Why I am doing that is even if whatever procedure I adopt for calculating the reciprocal vectors for 2D should also be valid when I stack all these 2-dimensional planes together to make a 3-dimensional crystal. So, it should be consistent. What I am assuming here is that these are stacked such that the distance between them is C, and C is perpendicular to A B plane, and let us say this is C times Z direction. So, I am taking this to be the A B plane to be the x y plane. Then the procedure is very simple, because then A 1 would be 2 pi B cross C divided by A dot B cross C, and since C is C z, I can write this as 2 pi B cross Z over A dot B cross Z, which I can write further as 2 pi B cross Z divided by Z dot A cross B. A cross B anyway is in Z direction. So, this is like magnitude of A cross B. Similarly, I can write B 1 as equal to 2 pi C cross A divided by B dot C cross A, which is equal to 2 pi Z cross A divided by B dot Z cross A, which is A dot B cross Z, and this is again comes out to be 2 pi Z cross A divided by Z dot A cross B. So, in 2D, I have A 1 which is equal to 2 pi B cross Z divided by Z dot A cross B, and B 1 which is 2 pi Z cross A divided by Z dot A cross B. So, let us see what does it do. Suppose I have this A and B like this with an angle theta less than pi by 2. B cross Z would give me a vector in this direction. So, this will be A 1 with some magnitude. Z cross A would give me a vector in this direction. So, this will be B 1. So, you see that the angle between A 1 and B 1 is greater than pi by 2. So, it opens up, the lattice opens up. Similarly, if I have this lattice A and B, then A cross Z or B cross Z would be perpendicular to B. So, this will be like this, and so this will be A 1, and Z cross A would be perpendicular to A. So, that will be like this. This angle becomes smaller. So, when you make two dimensional reciprocal lattice, then the corresponding vectors change angles. If the original angle is in the real lattice is less than pi by 2, it opens up, becomes greater than pi by 2, and vice versa. Here I should make clear that this is right angle, this is supposed to be right angle. So, this is how this happens. So, I like to leave a question for you, and that is, make Wigner-Seitz cell, which is Brillouin zone for different reciprocal lattices in 2D. There are 5 of them, so just practice it. and I am again emphasizing this Wigner-Seitz and Brillouin zone together, because in real space is called as Wigner-Seitz, and in the reciprocal space is known as Brillouin zone. Now, what was the significance of Brillouin zone? What we learnt is that for X-ray scattering, we get a bright spot if k n plus or minus g square is equal to k out square. This was for elastic X-ray scattering, so that the energy remains the same, and this gave you k n dot g is equal to g square by 2 plus or minus, does not matter, I will just take the plus sign. I could equally have written k out plus minus g square equals k n square, does not matter, then you would get k out dot g equals g square by 2. So, I can write it either way, and the reason is that when we made a Brillouin zone, let me just make it arbitrarily, then any vector that is k that starts from the center of the Brillouin zone and goes to the boundary is a possible direction of k out or k in. The reason being that the way Brillouin zone is constructed, let me make it at an angle so that it is shown better. So, let me make it again. I will make it at an angle. The G is from here to the next cell. This is G. So, this is precisely G by 2. So, K dot G, the projection of K on G is G square by 2. This automatically satisfies this. The other way of looking at it is that I can make a vector from K to the other side, and that is going to be G. So, this is related to the k in or k out, k prime. So, one of them would be k in, one of them would be k out, and they will be related by k equals k prime plus g. So, Brillouin zone gives you those k vectors for which I will see a bright spot during X-ray scattering, and that is the significance, geometric significance of Brillouin zone. This will also be important when we talk about band theory, because there the k of X-rays would be replaced by k of electrons, and there will be a band gap opening up at the boundary of Brillouin zone, because that is where the different G's or the different K's mix. The k which is equal to the k vector which is equal to from the center to the Brillouin zone boundary can be mixed with another lattice, reciprocal lattice vector, and that opens up a gap, and we will see that during the discussion of band theory. So, this is the significance of Brillouin zone. So, let me now go to X-ray scattering with all this background. we have k prime, which is outgoing wave, is equal to k incoming plus g, from which for elastic scattering we got k dot g is equal to g square over 2. So, first thing we want to do is show that this is equivalent to Bragg's diffraction condition. And what I would urge you at this point is go back to the beginning of previous lecture, lecture 17, where I had done diffraction of light and showed that when you take the Fourier transform of the grating, that gives you the same interference condition that is generally known as the grating equation. So, in this case, how do we do it? Now, recall that Bragg's condition was that if I am given a lattice, then we assume that the X-rays which are coming in, they are kind of reflected by these planes like a mirror, what is known as specular reflection. Specular means mirror like. And then you ask at what angle do they interfere constructively. This is in a way of interpreting this condition that we have derived, and we want to show that the two are equivalent. So, for this I take two steps. Step 1 is that G vector is perpendicular to HKL plane if G is equal to H A1 plus K B1 plus L C1. And remember that H, K, L are integers. So, this is a reciprocal space vector. How do we show that? If I look at the HKL plane, two of them the intercepts they have is A over H, B over K and C over L. I would like you to recall problem 4 from lecture 16. So, I have G, which is H A1 plus K B1 plus L C1, and I have these planes. And next one. So, this intercept is A over H, this is one direction, A direction. Along the B direction is B over K, and along the C direction it is C over K. So, two vectors in this plane which I am showing by red are going to be U, let us say, and V, and U is B vector over K minus A vector over H, and V vector is equal to C vector over L minus A vector over H, and these are two independent vectors in this plane. So, therefore, they span the plane. So, U and V are two independent vectors in the plane. So, if I show a property for these two vectors, that is going to be true for the plane also, because they are independent vectors. So, if I can show that G is perpendicular to U and G is perpendicular to V, then it is perpendicular to the UV plane. So, let us calculate G dot U. G dot U is going to be equal to A1 dot B. A1 dot B is by definition 0 minus A1 dot A, then plus B1 dot B, all of the cross products are 0. So, this is minus 2 pi plus 2 pi, which is 0. Similarly, G dot V is equal to C dot C1 minus A dot A1, which is again 0. So, G is perpendicular to U, G is perpendicular to V. So, G is perpendicular to UV plane. That is step 1. Step 2, distance between two HKL planes is 2 pi over mod G, and that is very easy to show, because if I look at these planes, two of them, the vector from one plane to the other in A direction is A over H, in the other direction is B over K and C over L. Projection of any of this vector along G would give you the distance. So, D H K L is going to be C dot G divided by mod of G. So, I am taking the projection of a vector from one plane to the other along the perpendicular, and that is the distance. Now, C dot G, this is C over A, C over L, is 2 pi, this is mod G. So, let me repeat this on the next slide. I have one plane, this distance is A over H, B over K, C over L, and the next HKL plane is like this. The distance here is A over H, or this vector is A over H, this is B over K, and from here to here is C over L. And I want to take its projection perpendicular to the plane. So, D H K L is going to be A over H times G over mod G, which is same as B over K dot G over mod G, which is same as C over L dot vector G over mod G. And this comes out to be nothing but 2 pi over mod G. So, that is the distance between the two planes. Now, what is our condition for diffraction? It is K dot G equals G square by 2. If I am looking at a plane and k is at an angle theta from that plane. So, this is my HKL plane. Then G is perpendicular to it. This is pi by 2 minus theta, and therefore, k dot G is equal to mod k mod G sine of theta. So, the condition out here gives me k mod G sine of theta is equal to mod G square over 2. K is nothing but 2 pi by lambda. 1 mod G cancels. So, I get 2 pi by lambda sine theta equals mod G over 2, and mod G is 2 pi by d. So, this gives you right away that 2 d sine theta equals lambda. So, what we have shown is that the condition k dot G equals G square by 2 is equivalent to 2 d sine theta equals lambda, which is the Bragg condition. What we need to show is that I should have 2 d sine theta equals n lambda in general. Before we do that, I want you to show that this result that d HKL equals 2 pi over mod G is consistent with the result of problem 4 of lecture 16. Now, how do I show that n lambda? Now, see what has happened in this case is I brought in a k, and this got out in k out, k in, and this was G. And this gives you k out equals k in plus G, and this deflection is 2 theta. I could have brought k in at a larger angle so that it rotates by 4 theta, and they are connected by 2 G's, G, G. This is k in, this is k out. I could have made the angle even bigger and make this connect with 3 G's. So, what would that give me? That gives me k equals mod G, there is a sine theta, over 2 times 1, 2, 3 or n, and that immediately gives me 2 d sine theta equals n lambda, and that is Bragg condition. So, all these conditions, Lowry condition, the evolved construction, the way we have derived this mathematical condition are equivalent to Bragg's condition. So, now what we have done is we have set up the entire mathematical machinery to determine crystal structure through X-ray diffraction. And how do we exactly do that? Whenever you have an X-ray coming in, I know the wavelength. What we need to do is somehow map all the planes of a lattice and match them. with whatever Brillouin lattice we have, and that will give you the crystal structure. They will tell you where exactly what all planes exist in that crystal, and there is a systematic way of doing it, and this is what we will be covering in the next lecture. What I would like to leave you with in this lecture is, try doing it. If a simple cubic crystal is exposed to an X-ray beam in all possible orientations, right? Either you can rotate it or have many crystals sitting there. Find 4 smallest theta for which bright diffraction spots will be found. If you try this problem, try to imagine what all is happening. This will put you on the path of how do we use X-ray diffraction and the X-ray diffraction pattern to find crystal structure. So, let me now conclude this lecture by saying that we have given the concept of Wigner-Seitz cell in real lattice and the corresponding Brillouin zone in reciprocal lattice, and then we have reviewed and discussed theory of X-ray diffraction. Thank you.